For our next lesson to the course, we're going to be talking about elastic potential energy, and we'll be starting it off with a definition of what a spring force is. If we take any spring, and whether this string is stretched or compressed, and take this string from its rest position, this string has stored energy called elastic potential energy. And this elastic potential energy is due to the force of the stretched or compressed string. If I picture for a moment, some spring that's attached to some mass. And we're going to call this at its resting position, so x equals 0. This is a relaxed state for the spring. So that means that my force of the spring would be equal to 0 newtons. And that is because the block, in this case, is at x equals 0. Okay, well, let's take another scenario here. Let's have x equals to 0 drawn around the same spot. And in this case, we are going to stretch out this spring. And when this spring is stretched, we say that our displacement, x, is in the positive direction. And we see from resting position that we have this displacement to the middle of the block at delta x. However, which way is the force of the spring going? And usually what the spring would like to do is it would like to go back to its relaxed state, its resting position. So our spring is going to go back towards the left at our relaxed state of x equals 0. And the same thing is going to happen if we have a compressed spring. We notice that we have our displacement from our resting position to the middle of the block right there. We see that we have it compressed in that it is traveling in the negative direction. And this would tell us in this case that our spring force would be going to the right in this case. So what we see, or what we can note, is that the direction of our force and direction of the displacement are opposite. And we are able to calculate the value of this the spring force, through Hooke's law. And Hooke's law merely states that the force exerted by a spring is proportional to the displacement of the spring. So mathematically, the force of the spring, Fx, is equal to negative k multiplied by our displacement x. And this negative k is simply our spring constant. And that spring constant corresponds to the stiffness of the spring. The stiffer the spring, the higher the spring constant. So let us see how we can practically use Hooke's law in a problem. And we have a mass of 0.250 grams hanging from a spring with a spring constant of 32 newtons per meter. Our mass is lifted so that the spring is compressed by 0.150 meters. And that's from the rest position. Calculate the acceleration of the mass when it is released. We are given our mass of 0.250 grams, which when we divide by 1,000 will give us 0.00025 kilograms. Our spring constant given to us is 32.0 newtons per meter. And we also have a displacement which is stretched, so it's in a positive direction, compressed, so 0.150 meters compressed, so we should make sure that that is in fact a negative. If we think about this scenario here, similar to what we were just drawing, we have our spring, and this mass is going to be released. So it is going to be accelerating forward. That is where our acceleration is going. At the same time, this means that our force on our spring is the only force acting on the mass, which is going forward as well. So therefore, from Newton's second law, we have that our spring force is equal to the mass multiplied by the acceleration. So negative k delta x is equal to m times a. And since we are solving for the acceleration, let us divide both sides of this equal sign, or of the equal sign, by m, so we can calculate our acceleration now. So that will be negative 32.0, our negative displacement, and all of that is divided by a mass of 0.00025. And we were looking to calculate our acceleration, and when we plug that into our formula, we calculate 19,200 meters per second squared. Significant digits, in my question, 3 significant digits the whole way. And since this is a vector quantity, we're going to say that this is traveling to the right, or forward as well you can use. Let's use forward. Forward sounds better. When we talk about the spring force, what else do we need to focus on? As I search drastically for a piece of paper. We want to make sure that we are aware that when we're talking about elastic potential energy, we are merely talking about the energy due to stretching or compressing an elastic material. And when we are talking about elastic potential energy, we know that we can calculate it, or I'm telling you right now, to calculate the elastic potential energy, we can do so merely by taking 1/2 k delta x squared. I'm not going to be too concerned about the deriving of this formula. We're going to make sure that we, in fact, know how to use this formula. And using this formula, say, for example, in a case when we have a spring-loaded toy, maybe, and this spring-loaded toy might be compressed, and it's going to eventually pop up from a table. And let's say it has a force of 35 newtons, and the toy pops up and is compressed by 0.012 meters. Calculate the elastic potential energy. How can we do so? So, I know that my force in this case was 35 newtons. My delta x is negative 0.012 meters due to the fact that it is compressed. It should be noted that we can calculate the force constant x, or k, sorry, by taking 35 over that displacement of 0.012. And since this is constant, we're going to maintain it as a positive, and our force constant, in this case, spring constant, would be 2,916.67 newtons per meter. So we're looking to calculate the elastic potential energy, EE. So 1/2 K delta X squared. So that will be 1/2 2,916.67 times negative 0.012 squared. And thankfully for the square, we do in fact get that our elastic potential energy will be positive in this case, and it is 0.2100. And when I observe this question, I look at my significant digits always when we do a calculation. Two significant digits. The elastic potential energy that's due to the compressing of this elastic material would be 0.21 joules. And one final little tidbit of information when we are talking about elastic potential energy. Suppose a mass attached to a stretch or compressed spring is released. What will happen? Well, when released, it will oscillate or rotate or go back and forth. And this oscillation back and forth, this type of motion, is a type of periodic motion. And we look at, in this course, or in this section, a special type of periodic motion, and that is simple harmonic motion, which we will short form SHM. Simple harmonic motion is merely a periodic motion in which the acceleration of the moving object is proportional to its displacement. We know it's proportional to its displacement if the force at its maximum peak amplitude is the highest there. And it will decrease our force as it comes back to its resting position. That's how we know we have simple harmonic motion. The force is greatest at the farthest distance away from its resting position and lowest when it's at resting position. And we can determine the period of a simple harmonic motion merely by taking 2 pi square root of m over k. And remember, t is the time it takes to complete one motion, and this will be our period in seconds. So what happens if a mass spring system does in fact undergo simple harmonic motion? And its maximum stretch has a elastic potential energy of 8.25 joules. A mass of 0.30 kilograms, and a spring constant of 228 newtons per meter. Are we able to calculate the frequency of this? Well, absolutely we are. I've given you the question. We need to know that calculating the period is quite easy, because as I had just mentioned, 2 pi square root m over k tells us that we can take 2 times 3.14 and take the square root of our mass of 0.30 over the constant of 228 newtons per meter. And when we calculate this, we would get 0.2277995. This is how long it takes to complete from resting position to its maximum displacement and back. Okay? To calculate the frequency of this, we would merely take 1 over our period, because frequency and period have an inverse relationship. So the frequency at which this occurs is 4.3898. Our frequency at this maximum potential energy is 4.4 hertz. But let's just look for 2 seconds just for fun. When does this maximum elastic potential energy reach? At what displacement from resting position? We can actually calculate that. We know that our elastic potential energy is 1/2 k delta x squared. Where is this maximum displacement? Where we have the maximum energy or maximum stretch of 8.25 joules. We can solve this by taking 2 times our elastic potential energy, so we got rid of the divided by 2. We must divide by k as well, because we want to get rid of the k on the right-hand side of the equal sign. And delta x squared, so we must take the square root to figure out what this maximum displacement would be from resting position. So this would give us 2 times 8.25 all over that spring constant of 228 would tell us what that maximum displacement is. And doing this calculation quickly, we see that our maximum displacement is 0.27 meters, or 27 centimeters. What this means in the simple harmonic motion sense is that if we have a spring that is stretched, that gives us our elastic potential energy of the 8.25 joules, that means that its maximum displacement from resting position is in fact 27 centimeters. And it would take 0.23 seconds to return from the 27 seconds back to its resting state.